Hi everyone, we're going to graph other trig functions beyond sine and cosine. In section 4.6, we're going to start with graphing y, or f of theta, equals tangent of theta. A key thing to remember, tangent is what? Tangent is slope. That's a great thing to remember. Tangent is slope. So for example, what is the tangent of 0 radians, or 0 degrees? The tangent of 0 is 0, which I'm indicating in purple here. I'm going to indicate the tangent values in purple. Remember, these are the slopes of these terminal sides. The tangent of 0 is 0. When theta equals 0, tangent is 0. The tangent of pi over 4 is 1. Think of the line y equals x. The tangent of pi over 4 is 1. And as we increase from 0 up towards pi over 2, the corresponding slopes are increasing from 0 up towards infinity. Likewise, as we go backwards, clockwise, from 0 towards negative infinity, the tangent of 0 is 0 once again. The tangent of negative pi over 4 is negative 1. As we decrease the angle towards negative pi over 2, the slopes become negative 2, negative 10, let's say, negative 100. The slopes are approaching negative infinity. And it turns out that we capture one cycle if we consider the open interval from negative pi over 2 to pi over 2. I'll discuss that in a moment. In the meantime, let's frame one cycle. All right. Now, one key difference from sine and cosine is that we're going to place our pivot, which corresponds to the origin. We're going to place our pivot right at the smack dab center of the frame. For sine and cosine, we would place the pivot at the left center of the frame. But among the 6 trig functions, tangent is the only one for which we put the pivot at the center. We're going to place the origin at the center. Bottom line, the key benefit of this is that we can represent a cycle by a single unbroken snake. All right, now let's see why the graph of this snake makes sense for one cycle of y equals tangent of theta. Well, again, tangent of 0 is 0. That explains why 0, 0, the origin, is on the graph. Tangent of pi over 4 is 1. That explains why this quarter point is on the graph. As the angle increases from 0 towards pi over 2, as the angle increases from 0 to pi over 2, theta, the tangent value increases towards infinity in terms of the y-coordinate. Now going backwards, tangent of negative pi over 4 is negative 1. That explains why this point, negative pi over 4, negative 1 is on the graph. It's a quarter point or key point. And as the angle approaches negative pi over 2, as theta approaches negative pi over 2, from the left, the tangent values, the slope values approach negative infinity. The y-coordinates, the tangent values, approach negative infinity. By the way, this all makes sense because remember, tangent is what kind of function? Tangent is odd, meaning the graph, including this cycle, is symmetric about the origin. If you take this snake and rotate it 180 degrees about the origin, you get the same snake. That explains, for example, why tangent of negative pi over 4 is negative 1, while the tangent of positive pi over 4 is positive 1. These 2 points are symmetric about the origin. These 2 points are symmetric about the origin. The graph of y equals tangent of theta is odd. And notice that when we graph this one cycle, we get 3 key points or quarter points, and we have 2 VAs, 2 vertical asymptotes at the edges, corresponding to theta equals pi over 2 and negative pi over 2. This here is our fundamental cycle for y equals tangent of theta. If we repeat the picture, we get another cycle, a snake from pi over 2 to 3 pi over 2, over here in dark blue. We have another snake here in purple from negative 3 pi over 2 to negative pi over 2. Again, the period for y equals tangent of theta is not 2 pi like before, it's only pi. The period is pi. The width of each cycle is pi units. Remember, the period is the width of a cycle, the thinnest piece of wallpaper, such that when you repeat it infinitely far in both directions, gives you the result of the entire graph for y equals tangent of theta in this case. What's another explanation for why the period here is pi? Well, look at the unit circle. Again, the period is pi, not 2 pi like before for sine and cosine. Well, look here. Think slope. Tangent is slope. As we go from negative pi over 2 to pi over 2, the angle theta, as the angle theta goes from negative pi over 2 to pi over 2, what happens to the slope? The slope goes from very negative to slightly negative to 0, tangent of 0 is 0, to slightly positive to very positive, very steep slopes, like a million, a billion. So we have this pattern of slopes or tangent values from very negative to very positive, covering this interval from negative pi over 2 to pi over 2. That's an interval of width pi radians. We have a distance of pi radians between negative pi over 2 and pi over 2 radians. But what about the pattern of slopes going from pi over 2 to 3 pi over 2? Well, again, it's the same pattern as from negative pi over 2 to pi over 2. We get slopes that are very negative, slightly negative, tangent of pi is 0. Then we get slopes that are slightly positive, and then slopes that are very positive, like a million or a billion. Remember that we always read slopes here left to right. So we have a negative slope or tangent value in quadrant 2, and we have a positive slope or tangent value in quadrant 3. But notice that this pattern of tangent values or slopes, again, we go from very negative to very positive, just as we did from negative pi over 2 to pi over 2. So basically, a half circle will give us a complete interval of behaviors for the tangent function. Very negative to very positive, and we get a repetition from here to here. So the cycle is only pi, not 2 pi. We don't have to go all the way around the circle to get a complete interval of behaviors for tangent. I would like to explain this frame in greater detail and how it's similar and different from the frames for sine and cosine that we did in 4.5. So what are some similarities? Well, again, we have this candy bar, this Kit Kat bar, 3 horizontal line segments this way, 5 vertical line segments this way. Those are similarities. We're going to get some key points on these intersection points. But there aren't too many similarities beyond that. We do split the period up into quarters. That's another similarity. But we more often notice the differences. What are some key differences with the way we frame this cycle? I'll do this. I'll put the writing over here and put the frame over here. All right, so what are some key differences? First of all, when we graph a tangent function, I should write out tangent here. When we graph a tangent function, the central point, the center point, not the left center point of the frame, will be our pivot, which here is the origin. And then later on, when we do translations and other transformations, it'll move around. But the pivot is at the center of the frame, not the left center like before. Also, the left and right edges of the frame correspond to vertical asymptotes, VAs. Graphs for our classic sine and cosine functions from section 4.5 did not give us any asymptotes. Here, we do get vertical asymptotes. In fact, we get them periodically, every pi units for the overall graph. And again, if the pivot is at the center, the VAs for tangent will be at the edges. Now, unlike for sine and cosine, the graph of a cycle will stretch beyond the frame and approach asymptotes. So sine and cosine graphs were trapped within the confines of the frame. They were waves. But these tangent snakes are going to break out of their frames, and they're going to approach these VAs at the edges. Notice that the range here will be what? The range here will be all real numbers. That was not the case for sine or cosine, the ones we did in 4.5. The cycles, again, are shaped like snakes, not waves. Although we do have these periodic cycles, we have a zoo of snakes separated by VAs, vertical asymptotes. And we have no maximum or minimum points. We do have inflection points. We do have these quarter points over here, but we don't get any max or min points for these tangent graphs, as we did for sine and cosine. Remember, sine and cosine waves were trapped inside the frame. These tangent guys are not. The range is all reals. For the tangent snakes that we draw, at least the way I do them, we get 3 key points and 2 VAs. Although if you move the pivot to the left center, what ends up happening, if you were to move the pivot at the left center, if pivot at the left center of the frame, like we did for sine and cosine, what ends up happening is that you get half a snake, a VA in the middle, and half a snake over here. We do get key points at the ends. So we end up with a half a snake, a VA, and half a snake. We would get quarter points also over here and over here. So what ends up happening is that if you put the pivot at the left center, like we used to, then we would have 4 key points and a VA right in the middle. But then we get this pair of half snakes. And although that is legitimate, this would represent a cycle for tangent of theta, it's not as appealing visually. I think generally speaking, we would prefer one unbroken snake as a cycle as opposed to these 2 half snakes. That seems a little gross, to put it mildly. Okay, so next time we're going to talk about domains, ranges, and equations for these vertical asymptotes. Next time.